Okay, everybody. So now we're doing section 2.3, rates of change, velocities and marginals. So what is the average rate of change? The definition of the average rate of change, if y is a function f of x, and the average rate of change is just going to be between a and b, it's just going to be f of a minus f of b over b minus f of b minus f of a over b minus a, which is really delta y over delta x, which is the average rate of change. So basically, you just figure out the value of the function at the left endpoint, and then the value at the right endpoint. That's b comma f of b, and this little diagonal line there. That's really represents the rate of change. So let's do it in a problem. So medicine, okay. So the concentration. Oops, let me just go ahead. The concentration C, which is in milligrams per milliliter of a drug in a patient's bloodstream, is monitored over 10-minute intervals for 2 hours, where T is measured in minutes as shown in the table. Find the average rate of change of C over each interval. So let's look at 0, 10. Well, 0, 10, well, that's when T equals 0, that's when T equals 10. And we see the concentration goes from 0 to 2. So it's basically just going to be 2 over 10, but let's just figure it out. So we say the value of C is 2 minus the value of C is at the left endpoint is 0 over 10 minus 0. This is basically changing y over changing x. And we get 2 over 10 pound. So it's 0, 20. Well, let's just take a quick look. So that's going to be 17 minus 0 over 20 minus 0. So it's just going to be 17 over 20. And between 100 and 110s, again, we just go to the table. That's 110, it says 103 minus 113 over 110 minus 100. Notice it's going to be negative. That's okay. It means it's getting less concentrated at that point. And pound. Now, why is it positive at certain points, negative at certain points? Ask a doctor. What do I know? I don't know science. I guess it's becoming less concentrated in the bloodstream or something. I don't know. Maybe it wears off after a while. That's all it is, just changing y over changing x. The average velocity, that's just change in distance divided by change in time. So let's take a look over here. A free falling object is dropped from a height of 100 feet. Neglecting air resistance, the height, which is in the variable s in feet, of the object at time t in seconds, is given by s equals negative 16 t squared plus 0. And the negative 16, I believe, comes from the force of gravity. But again, ask a physicist, not a mathematician. Find the average velocity of the object over each interval. So all you got to do is figure out where it is, what the height is when t equals 1, what the height is when t equals 2, subtract everything, and pow. So, but we're going to need a formula for that. So we have the formula s equals negative t squared plus 100. And what we're doing here is to make it easier, we're taking all the values, 1, 2, 1.5, 1.1, we're just taking all those values and putting them into this one table here. And of course, we'll do 0 as well. So when t is 0, the height, s is 100. How do you know that? Because it's, well, first of all, you can get it from the formula. Just plug in t equals 0. Second of all, it starts being 100 feet up in the air. Anyway, after 1 second, it's 84. And again, you just plug 1 into this formula. So it's 100 minus 16 is 84. At 1.1 seconds, it's 80.64. And again, just plug that into this formula. 1.5 and 2. So those is going, now it's going down, 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 which makes sense because it's dropping off a thing. So now that we have all these numbers here in this table, now we can get all our values. So for the interval 1, 2, so we have 2 minus 1 on the bottom, 36 minus 84 on the top. I'm taking that 36 and that 84. And we get negative 48 feet per second. And when t equals, the average between 1 and 1.5 is 64 minus 84 over 1.5 minus 1. Again, you just look at the values on the chart. And for 1 and 1.1, it's 80.64 minus 84 over 1.1 minus 1, which is it comes out to negative 33.6 feet per second. And that's the way, that's how numbers crunch out. Alrighty. Yeah, so notice that the velocities in that previous problem were negative because the object is going down. So it's based on that. Okay, well, that's average rate of change. What about instantaneous rate of change? Well, the instantaneous rate of change is, you figure it out the same way, but you look at the limit is, you look at as the interval gets smaller and smaller. So we're going to do a calculus limit. So we want the limit as delta x goes to 0 of delta y over delta x, which winds up being the derivative basically. It's the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. And of course, this is the famous formula for derivative that we all have tattooed in our brains. And the rate of change is called the velocity at that point, instantaneous velocity. So let's find the instantaneous rate of change or the velocity, if you will. So find the velocity of an object in example 2 at t equals 1. Well, we know the function, the position function. That's s is equal to negative 16 t squared plus 100. Taking a derivative, we're using the power rule. The derivative of t squared is 2t. 2t times negative 16 is negative 32t. The derivative of 100 is 0 because the derivative of a constant is 0. And pound. Now I just got to plug in. We said we want when t equals 1. We plug in t equals 1, and the answer is negative 32 feet per second. That is the instantaneous. That is the. Now what's interesting, if you look at the numbers here, negative 32. When you look at the previous problem, we're going from 1 to 2, 1 to 1.5, 1 to 1. Notice that these numbers getting negative 40, negative 48, negative 40, negative 33. These numbers are getting down closer and closer to negative 32. And that was kind of the trend. And calculus tells us that when it's, the instantaneous velocity is indeed negative 32. So it all makes sense. It all makes hideous sense. Alrighty, let's look at the next fun thing here. So the general position function for a free falling object is negative 16t squared plus v naught t plus s naught. S naught means is usually the initial height. V naught is the initial velocity. The velocity is going to change as the thing is falling, but that's the initial velocity. And the negative 16t squared, the negative 16 comes from the force of gravity. That's and gravity is, we're taking that to be a constant. I don't know if, it's more as a constant. Okay. Now the derivative is negative 32t plus v0. The derivative of velocity, by the way, is what we call acceleration. But I'm sorry, I take it back. S here is a position function. The derivative of position is acceleration, which is s prime. And I'm sorry. Oh, I keep saying the wrong words. The derivative of position is velocity. If I would take another derivative, if I would take the derivative of the velocity, then I would get the acceleration, but we're not talking about that right now. Anyways, so by the way, the acceleration due to gravity is negative 32. So the negative 16 is half the negative 32, in case you're wondering. Anyway, but again, I'm not a physics person, I'm a math person, so let's just move on. When t equals 0, a diver jumps from a diving board that is 32 feet high, as shown in this figure right here. That's the diver, in case you couldn't figure it out. The diver's initial velocity is 16 feet per second. So when he's up here, he's already going. Notice he wasn't just dropped, but he's going down. He's going down at an initial velocity of 16 feet per second. Actually, he goes up. It's positive 16, so he starts by jumping up. So the position of the diver is going to be negative 16t squared. That negative 16 is always there, plus 16t because he jumps up, and then plus 32 because he started out being 32 feet above the ground. Wow, that's hot. Wow, that's scary. So a couple of questions. When does the diver hit the water? And what is the diver's velocity on impact? Well, question A is really more of an algebra question. It's not a calculus question at all. All you do is you got to take this position and set it equal to 0. Set s equal to 0. See, because 0 is 0 feet off the ground, And negative 16t squared plus 16t plus 32 equals 0. And now we just do some basic algebra. So we either get t equals -1, which we're going to reject, or a t equals +2. So it's going to take the guy positive 2 seconds to hit the ground. Wow, that's he's going 2 seconds. That's probably 2 very long seconds. Now the velocity when he hits the ground, well, there you take a derivative, and since we know it takes 2 seconds, so now we can plug in t equals 2. So the velocity is going to be negative 32 times 2 plus 16, which is negative 48. Wow, he's going fast. Negative 48 feet per second. So his speed is 48 feet per second. His velocity is negative 48 feet per second. Because velocity is basically speed factoring in direction, speed and direction. Oh, that's scary. Wow, that's hitting the water pretty fast. Let's see how this works out in business. So we all know that profit is revenue minus cost, and how much money I take in minus how much money I spend to get that money. So P is profit, R is revenue, C is cost. Now there's something called marginal profit, marginal revenue. That's just a derivative. So dP dx is marginal profit, dR dx is the marginal revenue, and dC dx is the marginal cost. So whenever you see marginal in a business problem, it just means derivative. At least that's what I'm getting from this. And let's look at a problem here. So the profit in dollars derived from selling X units of an alarm clock is given by P is equal to 0.0002 x to the third plus 10x. We want to find the marginal profit for a production level of 50 units. And then we want to compare the marginal profit with the actual gain in profit obtained by increasing the production levels from 50 to 51. So let's just see what's going on here. So to find the marginal profit, we take a derivative, and the derivative becomes 0.0006 x squared, because and plus 10. That's the derivative of this guy right up here, because the derivative of x squared is 3x. The derivative of x to the third is 3x squared. But I multiply the 2 times 3, that's how I get that 6 from. And then the derivative of 10x is just 10. So now that I have the formula for the marginal profit, I just got to plug in x equals 50, plug it in, crunch, 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 and I get 1150 per unit. So the marginal profit at x equals 50 is 1150 per unit. Now, let's look at the actual profit. The actual profit is, go back to the original formula, which is 0.002 x to the third plus 10x. When I plug that back in, the actual profit is 525. That's when x equals 50. What about when x equals 51? When x equals 51, I plug 51 into the formula, and I get an actual profit of 536.53. Now, if I would subtract these two, I get 1153. That's the extra profit for 1 unit, and that's what it's saying here. It's saying here that the change is 1150. So it's not surprising that 1 more unit got me 1153. So that's kind of cool and awesome. So note that the actual profit increase can be approximated by the marginal profit, and that is very cool. And it's simply as marginal profit per unit. Well, that was very awesome. That was very, very awesome. Now there's something called a demand function, and that's P equals f of x, and so P is the demand. Now P is stands for price. Small p stands for price. Price per unit P is given by the demand function, and the total revenue related to the price per unit is revenue is XP, which makes sense. It's the number of units times the price. That makes a lot of sense. That's the revenue. That's how much money taken in. So we want to find the demand function. So the table shows what the units and the price in these years. And we want to use this information to find the demand function and the total revenue function. So first we're going to make a scatter plot. And here's the scatter plot right here, it looks like. Is this cell phones? I guess so. Let's see, where's his cell phones in there? Okay. Anyway, so it looks kind of like a straight line. And so from the graph, it looks like it's a straight line, which is a linear model. And that will be a good fit for the data. You know, it's never going to be exactly, but it's kind of pretty close. And to find the linear model, we use any 2 points. So we'll take 38,474 and 127,333. I get those points from here, and from there. And the slope connecting those 2 points is, if I just do the slope formula, y2 minus y1, x2 minus x1, I get negative 1.6 is my slope. So I'm going to use the point slope formula. So P is going to be negative 1.6x plus 535. And we, hold on 1 second. What did they? Hold on 1 second. Yes. Now you may be wondering, where did the 535 come from? Because I don't see 535 anywhere here. But the 535 is, let's see, which one did they use? They probably used, I don't know which one. Let's say they use this one. That's not 5, and okay, that'll be 5. So, oh, I see what they did. They took these numbers and they solved for P. That's what, you don't see a 535 up here because they take these numbers here and then they solve for P. All right, fair enough. So R is equal to XP, which is X times the P that we figured out from up here. So R is equal to negative 1.6 X squared plus 535X. And pow, that's our revenue function and that's our demand function. And all these things, and some of you, anyone here who's a business manager will understand a lot of this, the business aspect of this. Anyway, we have a fast food restaurant, and they determined that the monthly demand for hamburgers is given by this. So P is 60,000 minus X over 20,000. So figure 2.25 shows that as the price decreases, the quantity demanded increases. The table shows the demands for hamburgers at various prices. So here we see the different amounts of, this is demand for hamburgers, and this is the prices on the bottom. So we want to find the increase in revenue per hamburger for monthly sales of 20,000 hamburgers. In other words, find the marginal revenue when X equals 20,000. Well, we have the function here. To find, all we got to do is the marginal revenue is XP. So the marginal revenue is 1/20th of 60,000 X minus X squared. And because I just distributed the X into the parentheses, I pulled the 20,000 out. Now I just take the derivative. The derivative of this sucker is 60,000, plain 60,000 minus 2X. And again, don't forget the 1 over 20,000. And now we want to know what is it when X is equal to 20,000. Just plug in X equals 20,000, pow, and we get $1 per unit. That's the marginal revenue when X is equal to 20,000. And that is awesome. Okay, how about marginal profit? Well, you have a fast food restaurant. In example 7, the cost of producing X hamburgers is C, that's cost, equals 5,000 plus 0.56X, when X is in this range. I just want to mention that how they found these particular equations, that's a huge field. And that's a well-paying field to take raw sales data or take raw data of any kind and find a formula that fits that data is a huge field, and as a well-paying field. Anyone's interested in going into that. Anyway, so you want to find the profit and the marginal profit when X is 20,000, 24,000, etc. So first what we got to do is we know from example 7 that the total revenue from selling, the total revenue is this guy right here. And the total profit is R minus C. So we gotta just take the R minus the C. That's the R, that's minus the C, and that's gonna be our profit. Notice that here, the capital P stands for profit, small p stood for price, just saying. Anyway, if I just combine, multiply everything out, combine common terms, like terms and all that, and I get this guy right here, 3x minus x squared over 20,000 minus 5,000 minus 0.56x, and so that's the function right there for profit, I mean. So the marginal profit is just a derivative, which is 2.44 minus x over 10,000. Again, that's just the derivative of the sucker right here. Now, using these formulas, we can compute the profit and the marginal profit for all these guys. So profit, so when x is 20,000, profit is going to be 28,000. Marginal profit would be 2.44 minus that, and so forth. And again, what are the formulas? So that's the formula for this here is the formula. Well, this here, I guess, is the formula for P. That's the formula for this here is the formula for dP over x. And all I'm doing is taking those two formulas and just plugging in all these numbers, plugging in x equals 20,000, then plugging in x equals 24,000, plugging in x equals 30,000, and I get these, and I get these various numbers to spit out. So that is awesome, and that's kind of it. Now this is our we're gonna have wonderful homework now. I know you guys love the homework. You begged me, please give me more homework. Oh, we love homework. And I won't disappoint. I will give you homework, and I'm going to post that homework up on Canvas like I always do, and everything will be lovely and wonderful and fabulous. And we will see you guys next time. Bye, everybody. Bye.